Welcome to lecture 34. So, today we will do some backward integration. We have already done the hardest parts of type checking. So, we will just try to integrate it with whatever we already know about programming with our simple functional and imperative programming languages. So, always keeping in mind that it is possible often to do some static type checking, that is at compile time. Alright. So, when you come to general programming languages, the question of what is type checking? Well, in the case of the lambda calculus, of course, our type checking was entirely governed by the fact that all lambda functions, all lambda abstractions are unary functions, and so therefore, you had to do the type checking essentially only for unary functions, and since all other kinds of functions were sort of curried forms in the lambda calculus, certain issues were overlooked. So, essentially in its most general form, in an applied lambda calculus or in a programming language, type checking is just the fact that you have to check that each operation in the program receives the appropriate number of arguments of the appropriate types and in the appropriate order. So, the appropriate number of arguments was automatically taken care of in the lambda calculus by the fact that it took arguments one at a time, and each as and when an argument was obtained, it would have to type check. Of appropriate types was automatically taken care of in the rules for type checking in the lambda calculus. In the appropriate order was also automatically taken care of. However, in any applied lambda calculus where there could be n-ary functions, n-ary operations, what it means is that you will have to check all these things. So, for example, if the operation is not commutative or it is over a multi-sorted structure, then it all the arguments should come at appropriate times and should come in the appropriate order, and they should be all of appropriate types, right. The question is, of course, why do you require type checking? And probably the most direct answer is to answer the question, what actually happens without type checking. So, we already have an idea of what happens in the lambda calculus, in the untyped lambda calculus. What happens there is that well, any lambda term might be applied to any other lambda term, and the result is actually a lambda term, but you may not always be able to interpret it. I mean, so that's, and essentially the same thing happens in hardware. So, whatever may be the operation and whatever may be the arguments, the hardware, the underlying hardware, which is totally untyped. Of course, the difference with the lambda calculus is that the hardware is of course all of untyped data, bit strings if you like. The hardware always produces some result when types are not respected. Okay. And so for example, you could do integer addition on two arguments, one of them representing a character, another representing, let us say, a set. And what actually happens is, since the hardware is untyped, rather memory locations are untyped, registers are untyped, they are just bit strings. So, what can happen is that you will get something, and but the problem is that you will not be able to interpret the result. And in fact, this and that, the result of one type violation might actually be carried forward as an argument for another operation, and so on and so forth, which will continue to produce more and more meaningless results till the entire computation actually fails. And of course, this fails is a judgmental word. I mean, the hardware does not know anything has failed, and the question of whether it is failed or not really depends upon your interpretation, right. So, it will produce something, and it will be very hard for for the programmer to actually detect what exactly went wrong, right. Okay, so this the question of failure is not something that might be immediately detectable too. I mean, it's something that might come up years and years after the software has been sold for a phenomenal price to some unsuspecting customer who actually believed that it worked till something happened. Yeah. So, and so which means that so while it is true that you cannot get rid of all programming errors uh, in any foolproof fashion ever, what you can do at most is to introduce checks, and one important check therefore is type checking. Yeah. So, and you, since the underlying hardware is untyped, it's a good idea to introduce type checking among other things. So, type checking actually is a much more general term. For example, I would, when you look at array bounds checking in programming languages, that is also a part of type checking, because the index set for the array is a subrange type, and therefore you have to do type checking there. So, type checking is a fairly general word to catch a whole lot of issues, not necessarily all, right. And another unfortunate thing is that type errors are very common even among experienced programmers, and which means that early detection, if you can detect it early, then you can save a great deal of time and effort in wasted execution and in debugging, right. So, so even though what it means is that there is going to be a greater overhead on the compilation, it is often better to detect it early so that the production runs are not compromised. Yeah. Okay. So, otherwise what happens is the entire burden of detecting type errors or type violations, and type violations include things like array bounds checks and so on and so forth, is entirely on the programmer and during his debugging phase. Right. So, early detection implies that what we would like to do is actually detect it at compile time, and this is called static type checking. So, static type checking means that you do the detection of type violations as far as possible during compilation or translation time. Yeah. So, what this means is that compilation is slowed down, but it also puts in other things. I mean, for the type lambda calculi, you can do the type checking during translation time always, but it is not in general possible for for all features of programming languages. For example, it is only possible where you have statically created data. I mean, so that means through the mechanism of explicit declarations. So, declarations either before or after use, but declarations which clearly create places for data. So, dynamically created data cannot be, for example, statically type checked. So, any kinds of pointer mechanism, list mechanisms whose the data of which changes during runtime cannot requires runtime type checking or dynamic type checking. So, but for example, for most Pascal data structures which are static, I mean they have explicit declarations which give the full length, which give the full size of each piece of data. So, if you leave out the pointer mechanisms, every other piece of declaration in Pascal really gives you, you can compute whatever is stored in the activation stack is something that can be statically type checked. Whatever is going to be stored in the heap is something that will have to be dynamically type checked, right. So, an early type checking strategy means that as far as possible whatever declarations are there and which can be type checked, you do the type checking at compile time to save on execution time. For dynamic data structures, of course, you require dynamic or runtime type checking, and this is something, for example, Pascal actually has in the runtime descriptor in the for heap data, right. So, and of course, all this implies that you require whatever you can do static type checking only for statically created data, and it is possible only where where bindings are static. So, where bindings are determined at compile time. If there are bindings which are determined at runtime, then for example, in languages like Lisp and APL and Snowball, then what happens is that you can't do type checking at translation time, right. Okay, and so normally what happens is that all this type information is really what the information is really the information that is stored in the symbol table during the process of translation. Yeah, and so type information is usually some sort of attribute which is part of this symbol, which is part of the compilation process, and I mean that is how it is implemented, right. So, on the other hand, if you look at dynamic type checking, it's really something that has to be performed for each operation just before it is executed. As I said, I mean from the point of view of the hardware, an operation can always be executed and it will always give you some result. But if you want to ensure that type violations do not occur, then what it means is that you will have to perform this type checking before each operation is actually executed. So, there has to be code generated for checking. So, what it means is just that before you execute an operation, just check that there are actually the number of arguments that are required for that operation available. Each argument is of the right type and they are available in the right order. That's really all that it means. But the point is that a program is full of little operations, and what it means is that before each during execution you will have to do this checking before executing each operation, and that can slow down executions considerably. Yeah. So, this is also one. So, but however, what it does is it allows a sort of flexibility in language design. You know, it does not force you to do early binding, static binding. It allows, for example, well, declarations need not, I mean, it frees the kind of flexibility is also means possible abuse, right. I mean, that's an important thing to realize. Any kind of flexibility could also imply potential abuse. And so, which means that no declarations may be required in some of these languages which allow for a flexible typing mechanism whose type checking is done only at runtime. And then what more importantly, what can happen is that the types of variables may never remain static throughout their scope. I mean, they actually the types of variables may change during execution according to some need, according to some perceived need. But this has a price. I mean, there is a price to pay for these things, and what it means is that you can't take a printout of the program and expect to try to debug it to see what is wrong with it. What it means is that if you want, if such programs fail for some reason or give you results, unexpected results, what it means is that you will have to sit constantly with the debugger and try to determine what exactly is wrong with the program. Right. So, especially this type variables changing during execution can be very confusing for very large software. Yeah, and even for software which is just as large as a compiler, it can be very confusing and debugging can be very hard. Right. So, and then of course, the other kind of flexibility abuse that it allows is that it frees the programmer from typing concerns, but it makes debugging extremely difficult. And then what it the extra overheads that it adds when you have dynamic type checking is that you have to, if you, of course you could take the attitude that I do not require any type checking, it is too slow, forget about it, no type checking, but that means that there could be strange type operation strange type violations that might occur, and they might all actually produce results which on the surface look meaningful. Okay. But if you do want to do some type violation detection, then what it means is that if you decide to delay it to runtime, then what it means is that you will have to also tag every object with some type information to enable this kind of type checking at runtime. So, one thing of course is it means it often means a certain amount of increase in space, which may or may not be negligible, but what it more often does is that it actually slows down execution, right. So, most functional languages, most languages do some form of type checking, because even if when you look at their when you look at them as just forms of the lambda calculus, of the untyped lambda calculus, still they use operations of the underlying hardware, and there are representational differences and so on and so forth. So, they do some type checking in the applied in the underlying domain that to which they are applied, they do some elementary type checking. So, but when you do these things dynamically, what it means is that you are going to considerably slow down execution. Yeah. So, that is an extra overhead, right. So, now what we so type checking really is something that is not an absolute essential for programming, if you like, but it is a desirable thing to have in your translator or your runtime system. The attitude towards types has actually varied tremendously from the early programming languages, but more and more the feeling has come that really type checking is something that should be performed at some time before execution, which means either static or dynamic, mainly to detect errors in large software, right. So, it so the point so what has happened historically is that the early languages like Fortran had really no type except except integers and reals, but more and more typing information has been gathered. So, for example, with Pascal you get a fairly rigid form of static type checking with a certain amount of dynamic type checking to ensure that array accesses are not violated, array boundaries are not violated, and to ensure that heap data is, whenever it is created and destroyed, is of the appropriate type, right. In C, for example, there is an automatic possibility of casting one type into another, which is a type coercion, which is a form of type coercion, which is quite acceptable in many cases. You explicitly want to coerce certain types, but if you look at C++, again the rigidity of a Pascal typing system has again come in, which means that they have realized somehow that an early detection of type errors is somehow important to reduce debugging time, to reduce the overheads of runtime type checking. So, a large amount of C++ type checking is actually static. However, because C++ is a superset of C, any type violation, and every C program should be compilable, and executable in a C++ environment. I mean that's the basic principle. So, which means that the various kinds of abuse that you can do in C are also possible in C++ without any problems. I mean, so type abuse that you can do in C is also possible in C++. But if you were to restrict your C++ usage to just the standard libraries that are available with the C++ and just the C++ constructs that are new, then what you will find is that there is a tremendous amount of static type checking that goes on. One of the reasons why compilation in C++ is considerably slower than that in C. They actually do a tremendous amount of static type checking to ensure somehow that type violations do not occur, right. But the overhead, the typing overhead that C++ carries with it is the fact that it's got a very type flexible language, sub language, which is open to enormous amount of abuse, right. Okay, so let's carry forward our type inferencing mechanisms, or rather carry backward our type inferencing mechanisms, because we have done the hardest part of type checking. I mean, we know how to type check higher order functions. What we don't know is how to type check the underlying data. So maybe let's just finish that, right. So let's assume some elementary base types. For the present, I will just take the while programming language just to give you a flavor of how type checking can be performed, can be defined in a structurally inductive fashion. So that what it means is that you can actually do early type checking in many cases, especially for a statically scoped language. Okay, a statically scoped language means that the binding is early. The bindings are also static, and so type checking can also be done static. Memory allocation can be done statically for all except the dynamic data structures. So the type checking can also be done statically with relocatable addresses, whatever. So we'll just assume that our collection of types, which is actually, if you go back to the lambda calculus, what it means is that we are talking about the collection of base types. So it's just integers and booleans. It keeps it simple, and right. And then we'll use some symbol conventions. I mean, I'm changing one thing. I'm using this dark brown T to denote one of the Boolean values true or false, and T is of type bool, right. Then of course, I am using m and n as integer values. It is also even though I claim that the underlying hardware is largely untyped, very many architectures came up which during the 70s and 80s, which actually did at tagging an automatic hardware tagging of memory locations to do elementary type checking in a speedy fashion. So which means, what it means is that they would actually tag the memory locations to be either floating point or integer or boolean or character. They would just use these 4 basic tags, and everything else, all other type checking, especially for example of higher order functions and so on, was the compiler's responsibility. So they did use some form of either tagging or a separation of the elementary data types somehow to enable type checking to be performed, right, to enable at least basic type checking to be performed, not very sophisticated type checking, right. So and of course, we will have things like integer variables, maybe we will also have Boolean variables, whatever, right. And we'll for the moment we'll just assume that there is some way of determining types for the most basic constructs in the language. So which means variables, and I am not actually explicitly introducing declarations here, but ideally what you would do is you would introduce declarations, and that would be the explicit way of determining the types of variables at compile time and using them somehow to do the type checking for the rest of the program. But but since that is a trivial thing which I am not too bothered about now, I just want to give a structurally inductive definition of type checking without without worrying too much how the base types are determined, as they could be determined in several ways, right. So, and then we will, so what I am doing, the way I am changing the language now is that I have I previously defined two expression languages, an integer expression language and a Boolean expression language, and then a language of commands. Okay. In fact, what I did was I did the type separation in this syntax. So, what I will do now is I will mix up the syntax of expressions. One can't mix up the syntax of expressions with commands, but one can mix up the syntax of Boolean and integer expressions and see how type checking can be done. So, we will assume that that these Boolean operators are, I mean that these binary operators are available, and I will go ahead and also look for equality as being either between integers or booleans. These operations are integer operations. This is the only other Boolean binary operation. It is enough to have one representative of each kind actually. So, it is otherwise more than anything else it becomes boring to and repetitive. So, we will just assume that this is a suite of operations, and we will define the language and we will define what is known as a static semantics. Yeah, right. So, our expression language is somehow consists of all these expressions. So, essentially t is a truth value, m is an integer maybe. So, somehow let us assume that we can distinguish between t and m. I am not really bothered how. X is a variable, it could be a Boolean variable or an integer variable. Then this is a binary operation on expressions, it could be any of the binary operations we have said, and there is a unary operation, the only unary operation on expressions. The commands remain as they are. There is nothing much to commands. The only thing that I have done now is, from the previous incarnation of the while language, is that I have collapsed the Boolean expression language and the arithmetic expression language into a single language, which is just one set of production rules to enable, I mean to partly to ensure that we can actually do the type checking. That's about it, and it is not necessary to separate them very early in the at the level of syntax itself. It is possible to do the type checking and separate out what is well typed from what is not well typed. Yeah. As far as commands are concerned, expressions denote values, so they have a type. So, depending on what value it is supposed to return, it will have a type. Whereas, when you are looking at commands, commands just change state. Okay. So, commands really do not have a type, except that we should ensure that the underlying expressions are well typed. Okay. And we should ensure, for example, here, since there is no separation between Boolean and arithmetic expressions, we should ensure that you only have a Boolean expression here, right. And similarly for the while loop, right. So, the point is, so commands themselves will not have a type, we will just assume that there is a unary predicate of well formedness, which allows us to check whether a command has been properly formed with expressions of the appropriate type. And of course, a command at the top does not type check, or rather it is not well typed. I mean, this is a standard thing, is to say when something is well typed, it is, you say that it type checks. Okay. A command does not type check if any of these arms do not type check, or if this is, for example, not a Boolean expression. So, if this might type check to an integer expression, in which case of course the command is not well formed. So these are the elementary considerations, and which we will use for type checking, right. And principally we have to somehow be able to extract information about when an expression is a Boolean expression and when it is an integer expression. So that is fine. So now we will assume that somehow the base types are some either representation distinction or actually maybe through some declaration somewhere there is somehow some way of distinguishing the base types, which may not be entirely true on a bare machine. Yeah, right. So how does one type check expressions? Let's take the unary operation. If E is a Boolean expression, so what it means is that there are those type axioms like M is of type int and T is of type bool and so on and so forth already available, and if E is of type bool, then not E must be of type bool. I mean, and the point is that this can be done in a recursive descent fashion, right. And after the kind of complicated things we have done, all this actually looks really trivial, except that it seems more and more essential in programming languages to do this kind of type checking as early as possible. Yeah, even though it appears to be totally trivial. For any binary operation, what I am going to have is that if E1 is of type tau 1 and E2 is of type tau 2, then E1 binary operation E2 is of type tau 3, except that now I have to worry about what tau 1, tau 2 and tau 3 are. I have circled tau 1 in brown, tau 2 in sky blue and tau 3 in red. Okay. And now this rule is subject to these tables, which actually give you the type rules, right. That is really all. So, if you take the arithmetic operations plus, minus and star, if tau 1 is so what happens is an arithmetic operation type checks. So, tau 3 has to be integer only if each of E1 and E2 is of type integer. So, here is where it type checks. In all other cases there is a type error, right. So, this is the only non-error type, otherwise there is always some type error, and this is compile time detectable, right. So, if you look at equality, of course either you are comparing two booleans or you are comparing two integers. In all other cases there is a type error. Yeah. And in the case of OR, it is only when the two operations are Boolean that you actually type check. In all other cases you have an error, right. OR is meant to be a Boolean operation, so that is all. So this is all there is to type checking. Once you have dealt with polymorphism and so on and so forth, the hardest parts of type checking are really type checking higher order functions, for which you require the kind of heavy inference rules that we had for the type lambda calculus.
So the entry in the table are tau 3.
Yeah, the red entries are tau 3.
So equality of integer and integer gives
Oh, I am sorry.
Yes, Boolean.
Sorry, this has to be a Boolean. Right, I made a mistake there. Right, so this has to be a Boolean, and otherwise it is actually extremely trivial. The really hard part is type checking higher order functions, and once you have declarations available to you, you carry forward the type information in a static environment and you perform the type checking, just like you had a dynamic environment in which you did the execution, in which you wrote rules for the execution. So, you can look at the PL0 compiler, it essentially does similar forms of elementary type checking. And in the case of commands, all that we require is that we just have to go down deep into the command, that is it, right. And in a recursive descent fashion, we should just ensure that the commands are well formed, right. So, I would say that command C is well formed. I mean, I will use the predicate WFC to indicate that a command type checks if it satisfies these rules. I mean, the basic thing is that the assignment should be between things of compatible types. Okay. Now, in most programming languages, you have type coercion mechanisms, that means, or casting mechanisms from so that you can either explicitly or implicitly coerce, let us say, an integer value to be a real value, okay, or truncate a real value in order to give you an integer value, whatever. So, in many programming languages, including Pascal, actually the integer to real conversion is implicit. I mean, if the left hand side is a real variable and there are integers on the right hand side, then there is an implicit function which converts the integers to reals and then does the assignment. In languages like ML, they have actually made it explicit, right, which is actually, well, a good idea. I mean, in the sense that if it is explicit, then you know that the programmer actually knows what he is doing, whereas if it is implicit, it is not clear whether the programmer is aware of what he is doing. An extreme case is in the case of Fortran, where you do the division, you have the same symbol for division, and the same symbol is used for integer division and real division, and it is not clear when a programmer will make a mistake, when he will get a quotient which is a real number, when and especially with variables not necessarily being declared with symbolic conventions and so on. In Fortran, it was it is actually a complete mess in terms of readability, whereas most later languages actually allow for some form of implicit or explicit type coercion. But then that type coercion function, let us assume it is explicit, is really a function from, let us say, integers to reals or reals to integers. Truncation is a function from reals to integers, and given an argument which is a real, truncation, and then by the standard application rules of the lambda calculus, you get an answer which is an integer, and you can write out those rules for both implicit and explicit type coercions, right. And in the case of other commands, you just follow the normal forms of structural induction, and if these two commands individually type check, then their sequencing also type checks, and the if then else and the while just require this kind of checking. Their individual bodies have to type check, and it should be ensured that the expression is a boolean, then the individual commands also type check, right. So, type checking rules are usually quite trivial, and it is because they are so trivial, it is because they can be done so simply that you always recommend early, preferably static type checking. That will isolate errors early in the program. It is possible to do it most of the time except for dynamically created data. If you have a language in which you insist on declarations before use, you can do a large amount of the type checking can be done at compile time, and errors can be pointed out, right. And and it saves on execution time, it saves on having large runtime descriptors, it saves on generating code to do the type checking at runtime, and it saves on execution time. So, more and more languages actually try to do type checking early. So, the most recent languages actually do all their type checking early, and also that is also the reason type checking is one important reason why many languages have moved from dynamic binding mechanisms to static binding mechanisms, because then you can do the type checking at compile time, at translation time. You do not need to wait for runtime type checking. Yeah. So, the introduction of declarations brings in a certain amount of complication. So, let us just assume here now I will just get rid of commands and let us look at a purely functional fragment, an ML like functional fragment. So, then what it means is that you will somehow have to make a distinction between what has been declared now and what was free. What could be redeclared now, for example, in a fresh declaration. So, a typical typed declaration of, let us say, a value could be like this. Let us assume that the other expressions in the language are the same and there is just one extra construct, a let construct, right. And then of course, we have the normal declaration mechanisms, right, the sequencing of declarations, or rather if you like the pipelining of declarations, the parallel evaluation of declarations, or rather independence of declarations and nesting of declarations, right. So, now the only sort of complication it raises is to actually know what are the free variables in an expression, what are the bound variables. The moment you introduce declarations, it means you have a concept of free variables and bound variables. You have a concept of a variable being redeclared, and therefore, I mean, and in particular redeclared to be of a different type. So, therefore, creating a hole in the scope, and therefore, it has to be taken into account during the type checking process, right. So, so with a language with declarations like this, then what it means is that you have to give some structurally inductive definitions for what exactly is being declared and what exactly is free, right. So, let us look at free and defined variables. In a functional language, somehow they do not use the word declaration, they say it is a definition. So, I will use these two terms interchangeably. In an imperative language, it is called a declaration. Okay, so the declared variable in an elementary value expression of this form is just x. The free variables in this definition are all the free variables of E. Yeah. So, x itself could occur in E, but we know from our runtime semantics that x which might occur in E refers to an x that was previously declared, and this is a redeclaration of that x, is a redeclaration of x. So, E may or may not contain x, but whatever x it contains, it is not the same x as this, okay, which is being freshly declared, right. So, and in the case of sequencing of declarations, the declared variables are just the unions of the declared variables, and free variables of D1 semicolon D2 are just the free variables of D1 union. Of course, you could use the variables that were declared in D1 in order to have the declarations in D2, right. I mean, in expressions within the declarations in D2. So, which means you just exclude those variables which were declared in D1 from the free variables of D2. Yeah. So, and then in D1 and D2 there is the condition that there is a condition of disjointness, right, that the same variable cannot be declared in both D1 and D2 and cannot be used. So, their declared variables are just or their defined variables are just the unions of the individual defined variables in the declarations, and the free variables are also just the union. And in the case of nested declarations, what you have is that in a nested declaration of the form D1 within D2, what you are actually declaring is only whatever is in D2. If you remember, I said that since the declarations in D2 could be very complex, you abstract out some of the sub expressions, give them new names in D1 and use them, but essentially at the end of this declaration only the environment created by D2 is available. So, the declared variables of this declaration are just the variables of D2, and the free variables here of course are all the free variables of D1 union all the free variables are D2 which are not free in D1. Yeah, right. Finally, when in all this of course is meant to define the notion of free variables in the expression language. So, for all other expressions the notion of free variables remains unchanged, and what I mean by all other expressions, I mean expressions of the form E1 binary operation E2 or not E and so on and so forth. And in the case of a let construct, what you have is just that the free variables of this are just the free variables of E, excluding all the free variables of E which have been declared in D, and including all the free variables that are already in D. Yeah.
So, free variable D1 within D2, shouldn't it be minus declared variable D1?
Oh yeah, yes. I was wondering what was wrong with it. Yes. So it should be the declared variables of D1. Right. Right. Yeah. So, and now essentially we require just this much, and this notion of free and declared variables is what is going to be used as in processing declarations as a context. Okay. So, if you remember what I said about contexts, a context is just a collection of variable to type bindings. Okay. So, given a program for which you want to do static type checking, all the free variables in the program should have types available in the context. Otherwise, you cannot do type checking of the program. Inductively speaking, of course, a complete program does not have any free variables, but inductively speaking, if you go through a program segment within a larger program, all the free variables, let us say this expression is, let us say an expression is a particular program segment in a functional programming language, all the free variables in that expression should have bindings in the context, and the bindings defined by that context are exactly what you require in order to do the type checking for these expressions. Okay. I have already pointed out that the notion of context is very similar to the notion of a runtime environment. Okay. I mean, you use the same updation you use the fact that you have to look up the runtime environment each time in order to find values during runtime. In the case of a static, in the case of a context, you have to look at the static, you have to look at the context in order to determine types. You can't determine values necessarily, because you are not running the program yet, but you can determine types. Okay, and it has exactly the same structure, and you can reproduce using the notion of whatever is free and whatever is declared, rules for type checking statically, which are very similar to, well, rules for type checking in the lambda calculus, and which are very similar in some sense to the runtime environment mechanisms which we used. So, this whole type checking is, since it is going to be done statically, I mean whatever we have done is supposed to be static. So, this whole kind of semantics which deals not with values, but with only types, is called the static semantics for a programming language. This is something I have delayed a lot in coming to, but essentially if you were to look at in any modern treatment of programming languages, there is syntax, pragmatics, static semantics and dynamic semantics. So, whatever we have done using the environments rho and so on represents the dynamic or runtime environment, and all that semantics is the dynamic semantics, and whatever and a similar semantics that we define for type checking is static semantics. So, a complete language document, is really complete only if it defines the syntax, the static semantics and the dynamic semantics completely, right. So, I will stop here, and next time I will start on procedures.